Welcome to this explainer. Today, we're pulling back the curtain on one of the most high-stakes, invisible battles happening in the modern world. Literally, every single time you tap your card, click Buy Now, or transfer funds, a silent millisecond by millisecond race kicks off. You've got fraudsters constantly deploying new, super sophisticated tactics to steal money, and on the other side, financial institutions deploying absolute cutting-edge technology to stop them cold. So we're going to explore the step-by-step process of building a real-time fraud detection system for a bank, just to see how this incredible feat of engineering actually works under the hood. Think about that millisecond motif for a second. Everything we're about to discuss today, the data ingestion, the complex graph algorithms, the machine learning models, the final decision, it all happens in a fraction of a second. I mean, it happens before that little terminal on the shop counter even beeps and says approved or declined. The sheer scale and speed of this process, it's honestly mind-blowing. Okay, let's dive right into this. We're going to follow the journey of a single transaction by building this system out step by step. First step, ingestion with Apache Kafka. Then, pre-processing and KSQLDB. Third, real-time feature engineering. Fourth, complex event processing using Flink. Fifth, explainable AI. And finally, adaptive feedback loops. Step 1, ingestion, featuring Apache Kafka. Our transactions journey basically begins the exact moment a customer clicks buy, which sends a signal straight to the data layer. But remember, a bank isn't just dealing with your one transaction, right? It's dealing with millions globally, all alongside login events, geolocation pings, and device telemetry. And this brilliantly illustrates how it all comes together at the base level. To build this event-driven architecture, you absolutely need Apache Kafka. Think of Kafka as this massive, multi-lane digital highway. It's designed to capture high-velocity events from all those multiple sources, payment gateways, mobile apps, authentication logs, and it does it with incredible fault-tolerant durability. If a server goes down, no big deal. Kafka ensures no data is lost and the flow continues completely uninterrupted. It partitions and stores these streams, getting them all prepped and ready for the next layer. Moving on to step 2. Pre-processing and rule filtering. Because as you can imagine, raw data coming straight off that digital highway is pretty chaotic, so it has to be instantly cleaned before the AI can even touch it. Enter KSQLDB. You can think of this as the system's first bouncer at the door. It sits right on top of Kafka and continuously queries the streaming data using a familiar SQL-like syntax. Basically, it performs lightweight, immediate filtering over sliding time intervals. So for instance, if a user suddenly attempts 5 transactions within a fixed 10-minute block, what we call a tumbling window, KSQLDB can instantly flag that simple velocity violation. And it does this without needing to wake up the heavier machine learning models. Now, this pre-processing stage handles 3 really critical steps seamlessly. First, normalization. This scales numerical data, like transaction amounts, so they're all uniform. Second, categorical encoding. This takes non-numerical data, like say a merchant type or payment method, and converts it into a numerical format. We actually also use tokenization here to instantly anonymize sensitive data, like your actual credit card number. And finally, rule-based filtering. This just tosses out the obvious junk or blatantly known bad actors right off the bat. Step 3 is real-time feature engineering. So once the data is cleaned, tokenized, and formatted, a single transaction on its own still doesn't tell us a whole lot. To catch a really smart fraudster, the system has to enrich this cleaned data with deep historical and behavioral context. Now, what's really interesting here is the sheer difference in value between raw data and aggregated features. A raw data point is, well, it's just a timestamp and an amount. But an aggregated feature, that compares the amount to your daily transaction totals, your average spending habits, or your location consistency. Suddenly, an $800 purchase isn't just a number anymore. It's a massive deviation from a baseline of your normal behavior. Context is literally everything here. So to build that context, modern architectures use graph databases, which are pretty much the ultimate detective of the system. Unlike your traditional tabular databases that organize data in rigid rows and columns, graph databases map out accounts, devices, and merchants as interconnected nodes. They represent the data as a complex web, which, if you think about it, is exactly how modern financial ecosystems and sophisticated fraud rings actually operate in the real world. And because the data is structured as this web, we can unleash some seriously advanced graph algorithms. Community detections spots clusters of heavily connected accounts that might actually be a hidden fraud ring.
Centrality measures find the key nodes. Often those are the money mules acting as bridges between legitimate and fraudulent clusters. And pathfinding traces complex money laundering routes, exposing the flow of funds that traditional databases would simply miss altogether. Let's move to step 4 and see how this all builds up. Complex event processing with Flink. We've got our clean data, we've got our rich, graph-based context, and now we need a brain to make the final call. This is exactly where Apache Flink shines. Flink is basically the master investigator of the whole architecture. It specializes in stateful, low-latency computation and complex event processing. What this means in plain English is that Flink can remember past events and execute dynamic windowing. It can recognize complex time-based patterns, like, say, a card being swiped in New York, and then literally 10 minutes later, that same account attempting a login from a device in London. It holds the state of the stream to connect these seemingly disparate dots. And right inside Flink, the pipeline deploys an entire ensemble of machine learning models. It seamlessly integrates supervised learning, which looks for known fraud patterns based on historical flags, with unsupervised learning, which detects entirely novel, weird anomalies that we have literally never seen before. Flink runs these models simultaneously to score the transaction's contextual risk in real time. If the score jumps too high, boom, the transaction is killed instantly. Number 5. Explainable AI and transparency. Okay, here's the really fascinating twist in modern banking. Detecting the fraud just isn't enough anymore. If a bank declines a legitimate transaction, or worse, blocks an account, it legally has to be able to justify its decisions to human regulators and customers. So the crucial point is we can't just rely on a black box AI that says no without giving a reason. When building the system, financial institutions integrate explainable AI or XAI frameworks right into the pipeline. Tools like SHAP, Lime, and PFI are used to unpack the ensemble model's decision logic. They tell us exactly which features, maybe it was the location mismatch combined with the unusually high amount, that triggered the block. This guarantees transparency and stakeholder trust. And thanks to federated learning techniques, it does the whole shebang without leaking any sensitive data privacy. And the impact of this is absolutely huge. By integrating these user-focused XAI explanations, the system provides human fraud investigators with a clear, highly readable summary of exactly why a transaction was flagged. That reduces manual investigation turnaround time by a massive 32%. Investigators aren't sitting around guessing what the AI was thinking. The AI is literally telling them. And that brings us to step 6, adaptive feedback loops. Finally, we reach the last stage of our transaction's journey. What happens after the decision is made? Well, the system has to learn from its successes and its mistakes to prepare for the future. Modern systems utilize these brilliant self-adaptive feedback loops. When a human investigator reviews a flagged transaction and confirms whether it was true fraud or just a false positive, that feedback is instantly routed right back into the system. According to recent research on FinAI models, this automated, streamlined workflow reduces feedback capture overhead by 89.3%. The days of waiting months for data scientists to manually retrain and deploy a new model, yeah, those are completely over. It actually uses a specialized reinforcement learning approach to process all this feedback. Now, without getting completely bogged down in the heavy math, it uses something called decay-weighted importance sampling, which basically means the system prioritizes recent fraud patterns over old ones. It dynamically tweaks its own thresholds to care way more about the fresh, new tricks fraudsters are trying today. This specific method allows the system to adapt 43.7% faster to emerging fraud techniques, aggressively minimizing the bank's financial exposure. This quote really perfectly captures the incredible architectural leap we've just explored together. We have moved from slow, legacy batch processing, where a bank might realize you were defrauded hours or even days after the money was gone, to this state-of-the-art event-driven system. Kafka handles the flood. KSQLDB acts as the bouncer. Feature engineering and graphs provide the context. Flink and machine learning make the split-second call, XAI explains it, and the feedback loop learns from it. Which leaves us with this final thought. To protect us in milliseconds, these systems are building incredibly deep, nuanced, graph-based profiles of our behaviors, our locations, and our habits. It is an absolute engineering marvel that keeps our money safe. But it does make you wonder, what does the future of banking look like when these protective AI systems inevitably know our daily habits better than we know them ourselves? It's a really fascinating balance between ultimate financial security and hyper-personalized AI profiling. Thank you so much for joining me for this explainer, and keep questioning the technology that runs our world.